Okay, fine guys, let's start. So in today's class, we are going to see one of the test called as chi-square test. Okay, so it's called as chi-square test, and I would say this will be the last class in the statistics. Okay, so let's try to understand what is a chi-square test. So to start with, mm, yeah. So first of all, we'll try to understand a few things about the chi-square test. So till now, we are dealing with hypothesis testing for the means of various samples. Okay, but sometimes it is also necessary or desired to test the variances of the population under study. Okay, so let's we obtain certain variance for a sample which is different from the population variance. Now we need to find out if the variance are within the acceptable limit or not. Okay, fine. These are just the definitions. Okay, we'll see with an example. Okay, then you will understand it in a better way. So basically, okay, mostly chi-square test is used to find out what is the difference between the observed values, okay, and the expected values, okay, for categorical variable, for categorical variable. Okay, so if for a particular, let's say, for example, okay, just I'm saying there are uh, boys and girls in a class, and the favorite color for boys is, let's say, green, and favorite color for girls is pink. Okay, so these are categorical values. Okay, so based upon, and let's say there are 40 boys and let's say some 30 girls. Fine. So based upon this data, if at all you want to find out if there is any relationship between the number of boys and the color they are liking, okay, number of girls and the color they are liking, fine, something of this sort. Okay, so you can try to use chi-square test and find out if the relationship is existing between these categorical variables or not. Okay, so I would say with an example it will be better to understand chi-square test than the definition. Okay, so yeah, the chi-square test, yeah, first of all, why it's called chi-square is this word is there, right? Is this Greek letter word is called chi. Okay, this is called chi, and when you square it, it's called chi-square. Okay, and also let me just see. Okay, fine. So the chi-square test for a variance is a non-parametric statistical procedure with chi-square distributed test strategy that is used for determining from a particular value. So the same concept. So here you will have chi-square test statistic. Okay. So as I said in the yesterday's class, so now you will have some when you do chi-square. Okay. So when you do chi-square, so it's called chi test statistic. Okay. And the same concept, the p-value, everything will be same. Okay, so the test statistic of the chi-square for the variance is calculated as follows. Okay, this is a formula for the chi-square test statistic to calculate, where n is the sample size, s is the sample deviation, and rho is the population standard deviation. Okay, and if the chi-square is less than critical value, accept null hypothesis, else reject null hypothesis. Okay, see, if the chi-square, whatever the value you are going to get, this one, if that is less than the critical value, okay, so accept null hypothesis. Okay, why? So because you will have the graph over here, so if the critical value is somewhere over here, okay, and if your chi-square value is less than that, that means less than this. Okay, so then obviously here you will have null hypothesis. So if you are moving towards null hypothesis, we need to accept the null hypothesis. Okay, but if it is greater than, then you need to reject the null hypothesis. Okay, so that we will see. Okay, so similarly, just like other tables, T table, Z table, you also have chi-square table. Okay, and this is how chi-square table looks like. Okay, so here also similar to the T table, where you need to calculate with two things. One is a significance level, second thing is a degrees of freedom. Agree? So here also you have two things, degrees of freedom and the significance level. Okay, and next thing is, yeah, so we'll see an example, guys. For example, see here, the variance of a certain size of towel produced by a machine is 7.2. Okay, the variance of certain size of towel produced by a machine is 7.2 over a long period of time. A random sample of 20 towels gave a variance of 8. Okay, you need to check if the variability for towel has increased at 5% level of significance. Okay, at 5% level of significance, assuming a normal distributed. Agree? So a company is producing towels, okay, and size is 7.2. What is 7.2 meters or feet? Towel, it should be feet, right? I think feet, yeah. Okay, so 7.2 some units, okay, for a long period of time. So now you have suddenly considered just 20 samples, and that 20 samples gave a variance of 8. Okay, now you need to check the variability for the towel. Okay, that means what? If these 20 samples are giving 8, okay, does that mean the actual variance is actually 8? Is it increased or it is not increased? Okay, so that is a test you need to make over here. Okay, why? Because chi-square is mostly for the test of the variance, guys. Okay, chi-square test for the variance of a non-parametric statistical procedure. Fine. So over here also, as they have mentioned, it will say whether the variance of a sample which is different from the population variance. Okay, so we need to find out if the variance are within the acceptable limit, or does it varies more than the desired variance. Okay, so chi-square will be mostly revolving around the variance parameter. The other test will be mostly around the means. Okay, so over here, if you see, if you want to calculate this, so what is the formula we have? We have chi-square is equal to n minus 1 into s square by rho square. Okay, so what was that? Chi-square is equal to n minus 1 s square by rho square. Okay, so now what is n, guys? N is 20, number of samples, minus 1. Okay, into, okay, what is sample variance? 8, right? 8 by population variance is 7.2. Why? Because he's saying company is producing like towels with 7.2. That means this is a total population ka variance. From that, you took a 20 sample, and the 20 sample variance is 8. Okay, that's why sample variance is 8. Overall population variance is 7.2. 8 by 7.2. Okay. So what is the null variance? Null hypothesis saying it will be less than or equal to 7.2. Okay. So why? Because we want to test whether whatever he's saying is correct or not. Okay. So null hypothesis is considered as that is equal to 7.2, or that means it is not increased. In another way, he's saying it is not increased. That means either it is 7.2 or less than 7.2. But alternate guy is saying no, it is greater than 7.2. Okay, that means if you want to test whether it is greater than 7.2, okay, so you are not testing it is not equal to 7.2. It is, if it is greater than, so increased is just asking for increased. Okay, that means right tail test you need to do, one tail test, or in that right tail test you need to do. Agree? So once you put the formulas over here, okay, you got the chi-square as 21.11. Okay, so 21.11 is a chi-square. Okay, and what do we need in the chi-square? We need two things, guys. One is a chi-square, and second thing is a critical value. Okay, are we good till this point? Did you follow this example?
Yes, Santosh.
Yes, sir.
Okay, fine. So now you have chi-square. Chi-square is this value. Okay, just substituting in the formula, given formula. Okay, now we also want the critical value, guys. So, okay, once you have, you can compare both. So from where you are getting the critical value, as I said, you will get it from the table. But in the table, what you need, one is the significance level you need, and second thing is the degrees of freedom you need. Significance level, anyhow, you said at a 0.5%, that means 0.05. Agree? So he only said consider it as a 5% significance level. That means at 0.05. Now, degrees of freedom is what? Number of samples minus 1. Number of samples is 20. 20 minus 1 will be 19. So 19 and 0.05 will be our search value. Okay. So 0.05 is over here and 19 will be over here. Okay. So this value 30.14. Agree? So 0.05, 19. 30.14 will be our critical value. Okay. So yeah. So as you can see here, here also 19, 5 will be 30.14. Okay. So now you have this is called chi-square. Okay. Chi-square is what? Chi-square is how much? 21.11. Okay. 21 for example. Okay. And you have critical value 30. Okay. So chi-square is obviously less than critical value. Okay. So if it is less than, what I should do? Okay. If chi-square is less than critical value, accept the null hypothesis. Okay. So in this case, you need to accept the null hypothesis. Okay. And reject the alternate hypothesis. Now, what is null hypothesis saying? The variance is either 7.2 or less than, but it did not increase. Okay. So with this 20 samples, whatever you got 8, okay, that is only for that 20 samples. But actually the overall variance did not increase. It is just 7.2 itself. Okay. That whatever null hypothesis is saying, you need to accept it. Okay. So chi-square is less than the critical value, then we do not reject the null hypothesis. That means we should accept the null hypothesis. Is that clear, guys?
Yeah, Santosh.
Okay. So now, see, actually, that is a simple example regarding the chi-square, guys. So, but mainly chi-square is used for two types of test, guys. Okay. One is called as goodness of fit test. Okay. And other one is called the test of independence. Okay. So one is goodness of test. So where uh, see, the chi-square test is widely used to estimate how closely the distribution of a categorical variable matches an expected distribution. Okay. That means what? Distribution of a categorical variable matches expected distribution. That is goodness of test. Or whether two categorical variables are independent of one another. Okay. That is test of independence. Okay. So we will see these examples. Okay. But first, let's see goodness of fit test. Okay. So give me a second. Yeah. So goodness of fit test. Yeah. So as I mentioned over here, this example is for the goodness of fit test. Okay. So statistic number is a number that describes the relationship between the theoretical assumed data and the actual data. Okay. It is usually considered as a number of statistics that verifies the theoretical data set from the actual number. Okay. See, in the goodness of fit test, okay, as I said, there will be two types of test. One is goodness of test, and this is test of independence. Okay, these are two different applications where you can use chi-square test. Okay, so in the goodness of fit test, what we basically do is we try to estimate how closely the distribution of the categorical variable matches with an expected. Okay, that means you will have two things. You are observing some value, but actual value, that is expected value, is something. Okay, so how close are this? How close are the observed value and the expected value? Okay, this test can be done using chi-square, and that is called goodness of fit. How much your observed value is fitting the expected value. Okay, and for that the formula is this. Okay, see, the chi-square test for testing goodness of fit is used to decide whether there is any difference between the observed or experimental value and the expected theoretical value. Okay, a goodness of fit test is a test that concerned with the distribution of one categorical variable. Okay, the null and alternate hypothesis result is focus. Null will say the population distribution of the variable is same as the proposed distribution, and alternate will say distributions are different. So chi-square statistic is calculated as observed minus expected whole square by expected. Okay, so observed value minus expected value whole square by the expected value, and that you need to do it for summation. Okay, that means for all the different types of observe, if there are like more than one value, one categorical value, then you need to do it for each and every value. Okay, this will be plus for second observed minus expected whole square by expected, like that. Okay, so don't worry, we'll see an example, then it will be very much clear for sure. Okay, see, where you are having observed will be the actual count, and the expected is a predicted count. Okay, and let's see with an example. See guys, this example will give you a better understanding. See here. Okay, see, a survey conducted by a pet food company. Okay, a survey conducted by a pet food company is saying that determine that there are 60% of dog owners have only one dog. Okay, 60% of the dog owners have only one dog. 28 of them have two dogs. 12 have three or more. Okay, so out of 100 percentage of the dog owners, okay, he's saying 60% are having only one dog. Okay, and 28% of them are having only two dogs, and 12% of the are having three dogs or more, greater than three dogs. Okay, so this is what's the distribution that the pet food company has provided. But you are not convinced by the survey, and you decided to conduct your own survey, and you have collected the below data. Okay, so when the data you collected, you observed that out of 129 dog owners, okay, 73 are having one dog, 38 are having two dog. Okay, this is your data. So over here, when you consider 129, okay, so 73 are having one dog and 38 are having two dog. Okay, one dog, two dog, and the remaining how much, guys?
129 and 173 minus 38.
18.
18.
So 18 owners are having more than three or more. Okay, this is your data. Now determine whether your data supports the results. Okay, from this, based upon our data, we need to decide whether whatever the pet food company is suggesting or providing is true or not. Okay, so first thing is, see, this is a expected value. What is this? These are the expected values, 60, 28, 12. All those are the values which are set by the company, and that those are the expected. And whatever we have calculated by taking our own survey, these are all the observed values. Okay, so now first of all, if you see the expected value of one dog is 0.60 because 60% is okay. Expected value of second dog is 0.28. Okay, expected value of the third dog is 0.12. Okay, these are the expected values. Now what does the null hypothesis will say? Proportion of the dog is equal to survey data. Okay, why? You remember here the null will always say the proportion is same as a actual proportion is same as a proposed distribution. Okay, that means a variable or whatever the values we are comparing before and after will be the same, but alternate will say it's different. So here also null is saying the proportions of dog is equal to survey data. That means observed is equal to estimated is what the null is saying, and alternate is saying no, it is not equal. Okay, fine. So now the point is we need to calculate this. Okay, so our aim is to calculate we need to okay, so for that we need to calculate it for all the dogs. Okay, so as I said, if how many categorical variables you have, you need to do it for all. So you have three dogs, so that means one dog, two dog, three dog. Okay, so for one dog, what is the observed value is 73. Agree? So for one dog 73, this is your observed data. Okay, so 73 is one dog, 38 two dog, and remaining 18 for three dog. Okay, so observed for dog one, dog two, dog three, observed value is for 73, 38 and 18. Okay, total is 129. Okay, so out of the same 129, the expected value will be what? So in expected, they are saying 60% of them are having dog owners. So how much will be 129? 60%, 129 into 60 will be 77.4. Okay, so the actual expected from the company is saying 77.4 owners will be having one dog. Okay, and remaining what they're saying 28 is having two dogs. What will be the 28 percentage of 129? It will be 36.2. Similarly, in remaining 12% will be 15.4. Okay, so these are the expected values, these are the observed values. Okay, and now if you want to just put in the formula, see observed minus expected you do. Okay, so 73 minus 77.4 minus 4.4, 38 minus 36.2 1.8, 18 minus 15.4 2.52. Okay, observed minus expected, and you do square of this, square of this, square of this. Okay, so you get these values, and once you do this, then what you need to do, divide that by expected value. Okay, so this is a square and you need to divide this by expected value. What is expected value? 77.4. So it is 19.36 by 77.4. Why? See, square by again expected. So 19.6 by 77.4. Okay, again 3.53 by what is expected? 36.2. 3.53 by 36.2. Okay, 6.35 by 15.48. Observed minus expected whole square, right? So yeah, so I think there is a calculation mistake. Okay, so this will be 6.35 by 15.48. Okay, so what are the value you are going to get over here? Okay, so you can do the calculation. So for example, you got 0.7533. Okay, so this is a chi-square, chi-statistic, test statistic. Okay, are we good till this point, guys? Are you able to understand how to use this formula? Or shall I repeat?
Can you please repeat one, Santosh?
Okay, see guys, simple. These are the expected values. Expected percentage is already given. Okay, and first of all, this table is called cross tab table, guys. Okay, this table is called cross tab tables. That means in chi-square, first of all, you need to create this cross tab table. That means the observed versus expected table you need to create. Over here, what is that? Total three types of dogs. Owners having one dog, owners having two dog, owners having three dog. Okay, so over here just mention observed values. What are the observed values? My observed values are 73, 38 and remaining 18. Is it clear? 73, 38, 18.
Yes.
And after that, expected value. So out of this same 129, overall dog owners will be same. So out of this 129, company is saying 60% are owned by one dog. So what is 129 60 percentage? 129 into 60, right?
Okay.
77.4. Similarly, other values. Okay, so now these are the expected values. That means whatever the company is saying. These are all
Okay.
observed values from our survey. What you have expected, you have observed. Just put it in this formula.
Yes. Yes.
Okay,
Yes.
so once you put it in formula, you have and sum them, the summation and sum all those, you got some chi-square value. Okay, clear?
Yeah, Santosh. Clear.
Fine. So now once you do that, then you got chi-square. Chi-square is done. Okay, then after that, what is left? You just need critical value. Okay, now critical value from where you are going to get critical value will be from the table. Okay, so in this table, what you need degrees of freedom and level of significance. Level of significance is 0.05. But what is degrees of freedom? Okay, so see, use significance is saying 0.05, but from the degrees of freedom is what? Number of samples minus 1. So here will be number of categorical variables minus 1. How many categories we are considering? Three categories. One dog, two dog, three dog. Okay, 3 minus 1, 2. Okay, so that's why you need to go for degrees of freedom 2 and degrees over here and 0.05. Okay, 5.991. 5.991. Fine. So over here 5.99 will be a critical value. So now chi-square is 0.7 and critical value is 5.99. Okay, so obviously chi-square is very much less than the critical value. So in that case, we cannot reject the null hypothesis. Okay, that means we need to accept the null hypothesis. We will not reject. So whatever the null hypothesis is saying, that means what is saying, the proportion of the dog is equal to the survey dog, that is almost equal. Okay, Is it clear, guys?
Yes.
Okay. So this is yeah, regarding the goodness of fit test. So now we will try to see one more example. Okay, so let me go. Yeah, see here. So last lesson we introduced a framework of statistical hypothesis testing and t-test for investigation different numerical values. Okay, so in this we are going to turn our attention to one more categorical test called as chi-square test. Okay, that's fine. Okay, so over here, just give me a second, guys. Yeah. So over here, the same population example we are going to take, and in our the chi-square, yeah. So in our study for t-test, we introduced one-way test to check whether a sample mean differ from the expected mean or not. Okay, in one-way t-test, we are checking if one sample mean is different from the population mean. In the chi-square goodness of fit test is an analog of the one-way t-test for categorical variables. Okay, so it tests whether the distribution of sample categorical data matches with an expected data or not. Okay, for example, you can use chi-square goodness of fit test to check whether the race demographics of members at your school or church matches the entire US population. Okay, or for example, whether the computer browser preferences of your friend match those of the internet use as a whole. Okay, that means your friend's computer preferences, browser preferences is same as the overall population. That means, in other words, he's saying if a sample, okay, so how much the sample is similar to the actual value. That means how much observed values are similar to the expected value. Okay, so this example we will see. So whether the race demographics of a members at your school. Okay, so a small sample, a small school you have considered, and in this it will have some races, right? So from yesterday they are considering all these races. I don't know why. Okay, so all these races, white, black, Hispanic, so all these races from a small school, if you observe this, so you can do this chi-square goodness of fit test to check how much this is matching with the entire US population. Okay, so entire US population races. Okay, so how much it is matching between the small school sample. Okay, so that we are going to do. Okay, so now, yeah, so NumPy, Pandas, SkyPy, you're already aware. Okay, so now when you go to let's create some data set. Okay, so PD dot data frame. Here what you're doing, white you are taking as 1 lakh and Hispanic you're taking 60,000, like that, black 50,000, Asian 15,000, others 35,000. Okay, this is for the national. Okay, but if you want to consider only one state, Minnesota. Okay, in US I think there is states in okay, Minnesota, it's like if this is population, this will be a small sample. Okay, so if you consider this sample, so here you are taking, these are the proportions of the races. See, because it's a small state, you will have small values, 600, 300, 250. This is the overall population, nation. Okay, so now as I said, you need to create the crosstab tables for both of those. Okay, so how does this crosstab look like? Okay, so it is see, nations in national. So these are the races and these are its count, and for the sample or state, these are the what is it, races and its corresponding count. Okay, now we want to see, yeah, so now the chi-square tests are based on something called as chi-square statistic. Okay, same thing, observe minus expected whole square by this one. Okay, so over here, see, observed values are what? Observed values are our Minnesota table. Okay, observed values are our Minnesota table. Okay, because a small sample we are observing. Okay, whether it is a school or church, as you mentioned, or a small state, those are observed. Okay, but what is expected? The overall population, the national, is the expected value. Okay, so once you take the proportions, so over here you are having observed values equal Minnesota table. Okay, and the population proportions are what? So national ratios are national table. Okay, that means the overall national table by the length of the national. Okay, over there you will get the corresponding national proportions. Okay, what is national table? National table by the length of the national. Okay, you will get its proportional values, and expected values are national ratios okay, the same ratios into our particular state length. Okay, this ratio, whatever the ratio you are going to get over here, if you want to find the value for our corresponding state, okay, so that is our Minnesota. Okay, so you do it with the length of the Minnesota. Okay, so from here you are going to get the expected value and the observed value. Once you have the expected and observed, just put it into this formula, guys. Okay, observed minus expected whole square by expected, and do the sum. Whatever you are getting, that will be the chi-square test. Okay, so the value, whatever what you got is how much, guys? 18.19. Okay, 18.19. And chi-square assume that none of the test expects are less than 5%. That means it's a significance level of 5, or the confidence level of 95%. Okay, and this is your chi-square. Okay, this is your chi-square. And if you want to find out the critical value, okay, so one is a chi-square and one is a critical value. So okay, chi-square you got, how you got, so observed minus expected, so you observed values in Minnesota and expected values will be the this ratio. And if you want to calculate the critical value, so one thing is you can get it from the table as I was shown in the previous example. Okay, or you directly have the library. Okay, stats.chi-square.ppf. Okay, so from this you just give q equal to 0.95. Right, because 95% confidence level, and degrees of freedom equal to number of categorical variables minus 1. How many categorical variables you are considering? 5. 1, 2, 3, 4, 5. Okay, 5 categorical variables minus 1, that will be degrees of freedom. In similar example here, you have considered 3 categorical variables, dog 1, dog 2, dog 3. 3 minus 1 will be 2. That's why you have considered degrees of freedom equal to 2. Okay, so over here, number of categorical variables minus 1, 5 minus 1, 4. Okay, so once you do this, you get what is something called as critical value. Okay, so this is a critical value you got. And if you see, what is our chi-square? Chi-square is 18.19. Okay, so simply I can say chi-square is equal to 18. Okay, and what is the critical value? Critical value is 9.548. Okay, critical value is 9.48. So chi-square is greater than critical value. So obviously, what can I do, guys? Accept or reject?
Accepted.
Accept. Accept. Chi-square is less than critical value, then accept.
Okay, chi-square less than critical value. Okay, okay.
Okay, so these are the value. Area is different. Okay, see,
Yeah,
that's what I said. So when you're having normal distribution over here, if your critical value is this, okay, critical value is this. If your chi-square value is less than this, means what? Where it will fall? It will fall to the left side. Why? The values on this will be what? It will be like -3, -2, for example, -1, 0, 1, 2, 3. If you check the number line, okay, there is some critical value. Let's say it is 3, for example. And I'm saying chi-square value is less than this critical value. That means which side it will be? Left side or right side? Hmm?
right side.
Right side? This side? If I'm asking, see, now 3 is my critical value. So yeah,
Okay.
3 is my critical value. And if I'm saying my chi-square is less than critical value, so
Less
which
than
side it will fall?
left side.
Left side, right?
Yes.
So obviously it will fall this side. Okay, somewhere over here. Okay, so that means it is coming towards a null hypothesis, right?
Yes.
Right. In that case, we should accept.
Yes. Towards null hypothesis accept.
Right. These are the values. And but if I say our chi-square is greater than critical value is over here. But if it is greater than,
Yes,
means
sir.
it will fall over here. That means it
Right
is
side.
moving
Yeah.
away. So in that case, we need to reject.
Okay. Yes.
Is it clear, Meghana?
Yes, sir.
Getting right? So but this is values, guys. But if I say area is different. So but if I say, see, same thing, I think I know where you are getting confused. Value is value will be on this x-axis. Okay, if I say less than, it will be left side. If I say right side, it will be on the right side. But coming to p-value, if I say a small p-value, that means you are having only small area. That means you are moving to the right side. Okay, if I say p-value is keep on decreasing, a small p-value will be, that means you will move towards right side. Okay, see, if this is p-value, if again p-value is decreasing, means you will have only this much. Again, a small p-value, that means you are moving to the right side. Okay, when you consider p-value, which is an area, as a p-value decreases, you are moving to the right side. But if is a, but coming to the test statistic, if the value is decreasing, you are moving to the left side. There is a difference. Value is on the x-axis, area is on the, area will be what? This proportion. Okay, if the value is decreasing, what does that mean? We are moving to the left side. Do you agree? If the value is decreasing, you are moving to the left side, because the values to the left side are decreasing. 2, 1, 0, -1. And if the value is increasing, you are moving to the right side, because 4, 5, 6, we are moving this side, right? But if the area is decreasing, okay, see this side, what we are saying decreasing. Okay, this side what we are saying increasing for the value. Okay, but now p-value, for the p-value, if the p-value is decreasing, okay, that means you are moving this side. Okay, sorry, yeah, correct. If the p-value is decreasing, that means a smaller and smaller p-value will be where? Okay, see, if this is this, see, if this is a p-value, okay, this much is a p-value. Okay, so obviously you are here. If I say p-value is decreasing, that means you will consider only this much. That means you are moving this side, right? A still smaller p-value will be where? Only this much, still this much. Okay, that means what? If you are moving this side, the area is decreasing, p-value is decreasing. Okay, but if you move, if the area is increasing, that means this much area, p is increasing. Okay, p is increasing, still increasing, still increasing. That means what? So if the area is increasing, if area is increasing, you are moving towards a null hypothesis. In that case, you need to accept. Getting, guys? Are you following my words? See, I will repeat again. See, if the area is increasing, that means you are moving closer and closer to the null hypothesis. That means, see, this is only my area. P-value is what? Area. Okay, now I am only little far. Now this much is my area. Okay, that means this much. I'm moving towards somewhat closer to p-value. Sorry, null hypothesis. My p-value is again increasing this much. I'm closing still closer to null value. Now this much. Now this much. Okay, if my p-value is this much, all this area, the blue shaded, I'm moving closer and closer to null hypothesis. That means my probability, okay, to accept the null hypothesis is increasing. Okay.
Yes.
Right, so that means what? As I move towards the null hypothesis, my area is increasing.
Correct.
In that case, I need to accept. Okay, as I move towards my null hypothesis, my area is increasing. As I move away from the null hypothesis, my area is decreasing. Okay, that is one thing. But coming to the test statistic is not area, it is a value on the x-axis. Over here, as I move towards a null hypothesis, my value is decreasing, which is different from the p-value. In the both the case, see guys, there is a small catch here. Whether it is p-value or whether it is test statistic, if you are moving towards a null hypothesis, accept. If you are moving away from null hypothesis, reject. That is simple. Okay, if the value test statistic, okay, if the test statistic is getting lesser and lesser, that means from 3 it is going to 2.5 2. Okay, that means you are moving towards a null hypothesis. Okay, that means you should accept the null hypothesis. If you are moving away, that means if a test statistic is increasing, that means 4 5 6, okay, it is increasing. Okay, in that case you are moving away from the null hypothesis. Okay, in that case you need to reject. Okay, but coming to the p-value, it is other way around. Okay, so okay guys, I think I'll just draw a diagram just to clear the confusion. See, you will understand now. This is our distribution. I'm saying over here, who will stay? Our null hypothesis guy will stay here. Okay, now observe what I'm saying. What I'm trying to say over here is, you are having our test statistic. and this is our p-value. Okay. Now, let me try it. Increasing, decreasing. Okay. Clear. Now see guys. First of all, over here, okay, let's say this is some critical value. Okay, this is some critical value. Now, what this is values on x bar. What will be over here? For example, if I take simplicity, so let's say it is 0. Okay, if it is standard normal distribution, it is -1, -2, -3. Okay, over here it will be 1, 2, and critical value is 3. Okay, 4, 5, 6. Okay, now observe, if my critical value is 3, okay, and if my test statistic, okay, if my test statistic is this, okay, this is my test statistic. Okay, that means what? My test statistic is less than critical value. In that case, I need to accept the null hypothesis, because I'm moving towards null hypothesis. Critical value is over here. My test statistic is less than the critical value. That means 2 or 1. Okay, it is less than critical value. Okay, that means I am moving towards a null hypothesis. Agree?
Yeah.
Okay, so that's what he's saying. If the test statistics is so chi-square value or any test statistic is less than critical value, accept null hypothesis. Okay, so that means if your test statistic is less than, accept. That means what? If your test statistic is keep on decreasing, okay, a smaller value, for example, a smaller value of test statistic will accept the null hypothesis. Okay, so if the test statistic is increasing, for example, if my test statistic is increasing as 2, 3, 4, 5, should I accept or reject null hypothesis? Tell me.
Can you please repeat something? Test statistics?
See guys, observe my words carefully. I'm saying this is my test statistic. If my test statistic is increasing, okay, from 2, next 3, 4, 5, if it is increasing, should I
It's
accept
reject.
or reject?
Reject.
Reject. Okay. So if my test statistic is increasing, reject. Okay. If my test statistic is decreasing,
Accept.
accept. Agree, Meghna?
Yes, sir.
Or you agree, or you said it should be opposite?
No, sir.
Agree. Fine. So in other words, smaller test value is accepting. Okay, smaller value accept. Okay, larger value is reject. Agree? Small value, that means what? 2, 1, 0, that means you are moving towards null hypothesis. Smaller value you are accepting. Okay, but if you are moving away, that means if you are increasing, okay, if you are increasing, that means if you are moving away, you will reject. Okay, but larger value reject. Agree? Are you good with test statistic?
Yes.
Okay, now coming to the p-value, you see guys, p-value is what? P-value is the area. So now, for example, I will say p-value is, okay, in coming to p-value, let's say over here is our 0.05% alpha value. Alpha is over here. Okay, and if my p-value is very small, less than 0.05, that means only this much is my p-value. Okay, in that case, what I should do? Should I accept or reject?
Reject.
Reject. Okay, and if it is, okay, here it is reject. Now it is still lesser than that. Okay, earlier it was let's say 0.04, now it is 0.03. That means still small, only small part of this. Now
Reject.
0.22,
Reject. It is
0.1,
if it
less than
is
0.05, right? Less than 0.5, it is reject. That means if you are moving away, if you are getting smaller and smaller p-value, you are rejecting it with more evidence. Agree? A 0.04 p-value will reject. A 0.01 will strongly reject. Agree or not? A 0.0001, which is very much less than the alpha, will very strongly reject. Agree?
Yes, Santosh.
right? So as the value is decreasing, right, as the value is decreasing, what we are doing? Accepting or rejecting?
Reject.
Right, as the value is decreasing. So here the what is the value? It is not this value, it is the area. That's the reason p value is also the actual representation of p value will be area, guys. So if you visualize, try to understand p value from area perspective, it will always be simple and easy. So if the area is decreasing, that means smaller and smaller it is becoming. That means obviously it is moving away from the null hypothesis. Okay, so in that case you need to reject. But if the p value is increasing, okay, if the p value is increasing, that means now it is become, okay, now it is this much, next it is become this much, now it is increasing 0.5, now till here it is covered. Okay, so if this much area, okay, so it is increasing, so in that case what we need to do, we need to accept. Getting? That means what? A smaller value, a small value, a small value will reject. Why? A smaller value p will move away from the null hypothesis. Okay, but a large value, that means if the area is becoming bigger and bigger, that means it is coming towards the null hypothesis, which makes us to accept the null hypothesis. Okay, this you need to understand, guys. Okay, so a smaller value, so in p value what's happening? If it is becoming larger and larger, that means the area is becoming larger and larger, it is coming towards null hypothesis. Okay, with this one line you will understand. See, when I say p value is becoming large, that means what? The area is becoming large and large. Agree? The area is becoming large and large. That means it is coming towards null hypothesis. That's why you will accept. Clear?
Yes,
Yes.
sir.
Right? If the p value is area, if it is becoming larger and larger and larger, the area is increasing, coming towards null hypothesis, accept. But it is different from the test statistic. If the test statistic is becoming larger and larger, that means from 3, it is not area, it is a number on the y-axis, sorry, x-axis. Okay, so now here it is becoming large, that means from 3, okay, from 2 it becoming 3, 4, 5, it is moving this side. If it is becoming larger, that means what? It is moving away from the null hypothesis. In that case you need to reject it. Getting?
Yes, Santosh. Got it.
Yes, that's the way I'm trying to understand. Okay, and similarly if the p value is getting smaller and smaller, that means it is decreasing. Okay, from here, okay, if this area is keeps on decreasing, that means what? You are moving away from the null hypothesis, because area is decreasing, moving away from the null hypothesis. In that case you need to reject. Okay, but if you see the test statistic, it's a number. When it is decreasing, that means becoming smaller and smaller, means what? From 4 it is becoming 3, 2.5, 2, 1, 1.5, sorry, 0.5. That means what? It is coming towards null hypothesis. Because it is a number. When the number is decreasing, means it is coming towards null hypothesis. In that case, you need to accept. Okay, but the area is decreasing, means it is moving away. These two contradictory statements you need to understand, guys. If the number is becoming small, that means you are coming towards null hypothesis. But if the area is decreasing, means you are going away from the null hypothesis. Similarly, if the number is increasing, means on the test statistics is increasing, means you are moving away from the null hypothesis. But if the area is increasing, means you are coming towards the null hypothesis. Okay.
Yeah, Santosh.
Okay. So that's fine. Once we go back to our example, so over here you have something called as chi. What is chi-square, guys? Chi-square is 18. Okay. So you have chi-square is 18 and our critical value is 9. Okay, critical value is 9.48. Okay, and what is chi-square? Chi-square is obviously greater than critical value. So if the chi-square is greater than critical value, see guys, I said this is a critical value. Okay, somewhere it is our critical value, and our chi-square is now greater than critical value. That means what? It is to the right side or left side? Tell me.
Right side.
Great. Okay, so critical value is over here, and our test statistic, whatever is saying, that is greater than critical value. That means it's a number. So it is greater than means it will be the right side. Okay, somewhere over here. Okay, somewhere over here. Okay, so in that case, what should I do?
It's going right side, so it's a reject.
Okay,
Sorry. Yeah, reject.
reject. Okay,
Reject.
your answer, Meghana?
Reject, sir.
Reject. Okay, so that's why he's saying since our chi-square exceeds the critical value, we would reject the null hypothesis. Okay, the same thing you can also understand from the p-value also. See, p-value is saying 0.01. Okay, so with a confidence level of alpha is 0.05. Okay, and p-value is how much? 0.001, which is obviously less than alpha. Okay, so p-value is less than alpha. Okay, so what does that mean? P-value alpha is over here and p-value is less than alpha. That means a small area is having 0.001. Okay, a small p-value. In that case, what I should do? A small p-value.
Reject.
Reject, right? So in that case also reject. So you can always do it by two ways. One is by the critical value and the test statistic. Okay, so from the critical value and test statistics, you can compare and check whether you can reject, or from the alpha value and the p-value. Okay, from the alpha and the p-value also you can find out accept or reject, or from the test statistics or the critical value also you can take a decision whether you can reject. Both will give the same answer. Okay, but here critical value will be less than the test statistic will be less than. Okay, see the test statistic will be rejecting, right? So the test statistic will be greater than the critical value. That means you should move away from the null hypothesis. Okay, but see guys, there is a catch here. In this scenario, you have rejected in both the cases. Using critical value also you have rejected, using p-value also you have rejected. Agree? In both the cases, what happened? Did you observe? Critical value, see, our chi-square is greater than the critical value. Okay, chi-square is greater than the critical value. That means what? Our critical is just 9, chi is what? 18. Okay, that means what? It has moved away from the null. Okay, moved away. Agree? And p-value also, it is 0.01, 0.001. That is also small value. P also moved away. Okay, P also moved away. So we are going to reject. That means in any which case, if you are moving away from the null hypothesis, whether it is test statistic or p-value, if you are moving away from the null hypothesis, you will always reject it. Okay, but when you will move away for a test statistic, if the value is more, then you will move away. But if a p-value, if the area is less, then you will move away. That's the only difference. But in both the cases, you will move away. Okay, this logic you need to understand. In the both the cases, you will definitely move away, but the way how you are moving away is different. In the test statistic, if the value is more, that means see the value is more, that 18 is more than critical value. In that case, you will move away. Okay, in the p-value, the area will be less. Okay, the area will be less, 0.01. In that case, you will move away. Okay, so that's why if you are increasing the test statistic, you will reject. But in the p-value, if your value is small, that means you are decreasing the p-value, you will reject. Okay, in that case, both the cases you can conclude that the null hypothesis can be rejected. Okay, and alternate can be accepted. Is it clear, guys?
Yeah, Santosh.
Right. So same thing. So whatever we have done, that is manual calculation. So but however, you can directly use this stats.chi-square and just give your observed and expected value, guys. Same thing you are going to get. Okay, so the statistic array and the p-value. Okay, so this is just for your understanding. Okay, but if you want to calculate in one shot, so see, you can stats.chi-square. So you got 18.19 will be your count. Okay, that means that this chi-square, and your p-value will be the 0.01. Okay, so directly you can get it using this also. Agree? So that is regarding the, I would say, what the goodness of fit test. Okay, so one more test you have, we will quickly try to discuss this. Okay, it's called test of independence. Okay, so the chi-square test of independence test whether two categorical variables are independent or not. Okay, so it will say whether the two categorical are independent or not. That means, for example, you see the month you were born probably does not tell you anything about the web browser you use. Okay, so there is a date of birth month. Okay, so month you are born. Okay, month of birth and your browser you are using. There is no relation between that, right? And for example, your month of birth might be related to whether you are excelled at sports in school, or month of birth and sports might not be independent. Okay, is it real, guys? I have my doubts, because is there any relationship between the month of birth and the sport which you are playing?
No, Santosh.
Okay. Oh, okay, we'll see. So now in this scenario, the same thing example we are considering. Okay, so randomly I'm picking up Asian, Black, Hispanic. Okay, so these are my races. Okay, and these are my whether the people are Democratic or Independent or Republican. Okay, so these are my ratios of the party. This is a race and this is my political party. Okay, and as I said, you need to create a cross tab for the chi-square test. Okay, what is a cross tab? Cross tab will just say in ration, how many Democratic are there? Okay, see, he's saying Democrats will be 4%. Okay, so see, guys, the way how you need to understand here is out of 1,000 people, you are creating Asian with 0.05 percentage. That means how much percentage? How many people is 50? Agree? Out of 1,000 people, create Asian with a probability of 0.05. That means how much count you will get out of 1,000? What is 0.05 percentage?
5 by 100 into 1000.
50 or not? 1,000 into 0.05, guys. 50. Directly you can do it. 1,000 into 0.05. Okay. So the Asian count is 50. Doubts?
No.
Okay. Fine. So this is the sample, guys. Overall sample, 1,000 samples you take. In that 1,000 sample, how you want to divide? 0.05 to Asian, 0.15 to Black, 0.25 to Hispanic, 0.05 to other, 0.5 to white. That is what how we are creating data. Okay. So 0.05 is 50%, 50 values we are taking it for the Asian. Okay. So now in this 50, what is cross voter party is saying? Voter party is saying 0.4% will be Democratic. Okay. That means 4% of 50. How much it will be? 20.
But here we can see here also size is 1000. I thought 0.4 into 1000.
That is overall. See, overall you will have 1,000 Democrats, but that 1,000, see, that is correct. Good question. So 0.4% from this overall. But again, when you combine these two, this 0.4% will coming from, see, 1,000% is 1,000 people. From that 0.4 means how much, guys? 40?
400, right?
400, yeah, sorry,
Okay.
400. Okay, that 400 you will get from where? Some from Asian, some from Black, some from Hispanic, some from other, some from white.
Yes.
Okay, the overall
Yes.
that will be combined into 400. Okay, so in that 400 also you will have some share for the Asian from
Asian.
Hispanic, right? That share, the overall Democratic will be 400. That's fine.
Okay.
Okay, the overall independent will be 200 and overall
So we
Republican will
need
be 400.
Asian Democratic. We
Yeah,
need
correct.
Asian
Exactly.
Democratic.
Asian Democratic. Okay, that's what this is mean. Asian Democratic will be 21.
Okay.
Okay, the overall will be more or less 400 only, because if you see Democratic value is 397, almost 400. Agree? See, only Democratic is 400. Getting? These are the Democratic values. If you add all this, you are having 400, almost 400. Okay, Independent 190, 186. That means 2% means how much of 1,000? 2%, 200, nearby 200. Republican again 4%. That means around 400, 400. Okay, but this 400 is sharing between all of these these races. So you will have Asian Republic, Black Republic, Hispanic, like that. Getting? The overall value will be 1,000. Either you take this values is the all races also you will get 1,000, and all Asian or black also you'll get 1000 because both are thousands. So you only need to calculate the corresponding ratio. Asian Democratic is how much? Asian Democratic is 21. Okay, black independent will be 25. Other Republican will be 15. Like that. Okay, you can do calculation, guys. Okay, so you can check the calculation. Is it clear?
Yeah, Santosh, continue.
Okay, so after that, once you create the cross tab, okay, so these are the values. So over here, now if you want to do the test, okay, if there is any relationship between this voters race and the party, okay, so for the test of independence, use the same chi-square formula that we use for the goodness of fit test. The main difference is we have to calculate the expected count of cells in 2 dimensions instead of 1 dimension. To get the expected, multiply the row total of the cell by the total column and divide by the total exceptions. Okay, so fine. See, same formula you are going to do it for here also. See, expected values, okay, voter tab, so this you can take it as okay, this is fine. And yeah, so the chi-square test, the chi-square test is what? Observed minus expected whole square by expected. Okay, so observed values are the actual values. That means where are we getting the observed values? The actual value should be the observed values, guys. Where can we pick? Okay, let's try to understand this particular part. So the main difference to get the expected value, multiply the row total for that cell by the column total for that cell, and then divide by the number of observations. Okay, so see, row total, see, for the Asian, what is the row total? 60. Okay, for the Asian it will be 60 divide by what is the to get the expected value, multiply the row total for that cell by the column total. 60 into what is the column total? Column total is 397. Okay, 397. Okay, and then divide by the total number of observations. Total number of observations are
1000.
no, for
Total
Asian
number of
Democratic, for
observations.
only Asian Democratic, for
Okay.
only Asian Democratic, the row total is 60 and the column total is 397. Okay, so multiply row total by column total and divide by the total number of observations. Observations are 21. Okay, so you will get some value. Similarly, if you do for the white and independent, it will be the row total is 497 and the column total is 186 and divide by 96. Okay, you will have some value. Okay, so these are the actual values. Okay, these are the observed values. Sorry, these are the expected values. Okay, give me a second. So what are these values, guys? Okay, these are the observed values. Okay, fine. So to get the expected values, you need to do this calculation. What is that? Row into column by the observed value. Okay, so that will give you the expected values. And once you get that expected values, okay, so here he's saying what he's saying is this is for the Asian, how much he's saying? Asian is saying 60 397 by 21. Okay, so yeah, calculations, if there are any difference in the calculations we can check, but just try to understand the concept, guys. Okay, so actually there is one more example also for chi-square test. Okay, I will share you with that also, but the formula will be the same. Okay, so the expected values, okay, from the data frame, expected values are those. Okay, and now you can follow the same steps we took to calculate the chi-square statistics, to calculate the p-value and critical value. What they are passing, observed value minus expected whole square by expected value, right? But I'm just checking from where did they get this. Oh, okay, sorry. So okay, this will be the observed value. Okay, Asian and Democratic is 21 and this is the expected value. Okay, so now if we do, let's quickly try to do it for this example. Okay, so what is these are the expected values. What is the observed values of Asian Democratic? 21. Okay, so 21, chi-square will always be positive, guys, because we are squaring, right? So 21 minus expected is what? 23 minus 820, okay, into 2.82, right? 2.82 into 2.82. This will be the observed minus expected whole square divided by expected divided by 23.820. 23.820. Okay, 0.33 will be the value for Asian, guys. Okay, for Asian Democratic, it will be the 0.33. Okay, similarly, you need to calculate it for every other value. Okay, so these are the observed value, guys. I'm not sure if you guys understood. Sorry if there was some confusion. Okay, see, these are the observed values, guys. Okay, from these expected values, how you can calculate is, as I said, row minus row into column by the expected observed value. Okay, so once you get understand that these are the observed values and if these are the expected values. Okay, so the formula is same, the same concept we are doing. Okay, but calculations I'm not going into depth. Okay, same example, the dogs and owners example. So right, so you can consider observed value expected and do the observed minus expected values. Okay, so take this value any particular, for example, Hispanic independent, what is the observed value? 50. Okay, and Hispanic independent is 46.486. okay, this became expected. Now you have observed value. Okay, so sorry, now you have observed value, you have expected value. You can simply put in observed minus expected whole square by expected and do the sum like that. Do it for every value. You got some chi-square test. Is it fine, guys?
Yes, Santosh.
Okay, so you got the chi-square test as 7.16, and from the if you calculate the critical value, okay, if you calculate the critical value, 2 3 4 5 4 5 6, okay, what was the critical value there we are having? 15.5. okay, so 15.5 is a critical value. Okay, so chi-square is 7 chi-square is sorry, chi is 7 and critical is 15, which is chi-square is obviously less than the critical. What we should do, Meghana, should we accept or reject?
Less than means accept.
Perfect. Okay, so in this case, accept. So if we, in other way around, I'll ask C, we are accepting. So if we are accepting null hypothesis, what will be the p-value, guys? Can you guess what will the p-value? Will it be less than alpha or greater than alpha? That means alpha is 0.05. So p-value will
greater
be
than
greater than or less than 0. Greater
It
or
is
less than 0.05?
greater than.
Okay, it will be greater than 0.05. Okay, so you can see here the critical value is 15.57. So here you are accepting. Similarly, from the p-value also, can you see 0.51? 0.51 is also obviously greater than 0.05. Okay, that means bigger area, and also this is smaller critical value. Okay, so in that case, you are accepting the null hypothesis. Okay, so that is how you can do the what do you say, the degrees of freedom, sorry, the chi-square test, guys. Okay, and see, did I see the degrees of freedom over here? How you are going to get is mentioned over here. So you need to do number of categories minus 1, right? So here, how many categories you are having? So here you are having 5, here you are having 3. Okay, so number of categories 5 means minus 1 will be 4 and 3 minus 1 will be 2. So 4 into 2 will be 8. Is it clear? In earlier case, if you are taking only, if see, in this case only one category you are considering, 1 dog, 2 dog, 3 dog, so it will be 3 minus 1 2. That's why degrees of freedom is 2. But here you are looking at the 2 categories. One is the race, one is the voter party. Okay, so you need to calculate individual degrees of freedom. 5 overall samples, my categories 5 minus 1 will be 4 and 3 minus 1 will be 2. 4 to the 8. Is it clear?
Yes, Santosh.
Okay, fine. So that's how you can calculate those guys. And similarly, if you don't want to do all this, just say stats dot chi-square contingency and pass the observed values, and you will have the same value. So whatever the chi-square test, you have 7.16 over here, and the p-value 0.51, 0.51. Okay, and this is just the table which we got. Okay, 23.82. See, 23.82, whatever the values, the expected value. So here it is more better, right? So if you just pass the observed value, See, you are just passing the observed value. What is observed value? These are my observed values. Okay. So if you just pass the observed value very beautifully, it is only calculating the expected value. So this table 23.8 to 11.16 is this table 23.8 to 11.16. Okay. The expected value also it is giving, and based upon that, it is also giving the chi-square and also the p-value. Okay. So everything you are just getting from this one single line chi-square or contingency. Okay. So I would say that is regarding the chi-square test, guys. So if it is somewhere if you are missing, so I would recommend just go through the class. Okay. The logic will be just same, how to accept or reject null hypothesis. Okay, but mainly it is used for from the categorical data types. Okay, fine. So I would say that's regarding the stats, guys. Okay, and this test. So yeah, so you I would say just go through the class once again if any particular test is not clear. Okay, so but most of the modules which are required so are covered, including ANOVA and also chi-square test. Okay, yeah. Suppose that actual tomorrow plan is to start with the what NumPy, but I have observed that we have one more. I feel that you guys need to have some knowledge on something called as linear algebra also. Okay, so we have something called as linear algebra, so where we will be working on different matrices, guys. Okay, matrix multiplications, because in ultimately in machine learning, when you study that, you will understand that everything is a matrix multiplication. The whole deep learning is matrix multiplication, nothing more than that. Okay, the algorithms is just combination of different values matrices. Okay, so you should have some basic knowledge of matrices, okay, and some linear algebra. So tomorrow class I am going to give you some information regarding the linear algebra for specifically for data science related. Okay, and post that. Okay, so freshly we are going, so that will be Friday, and freshly we are going to start NumPy from Monday, guys. Okay, so from Monday we will start NumPy, and then we will continue pandas and matplotlib. Okay, is that fine, guys?
Yes, sir.
Okay, perfect, awesome. Okay, thanks, guys. So I just one thing I would say before going completing the stats module. Okay, so yeah, I would say I really appreciate. Okay, so because you are able to understand most of the things, okay, which is very good actually. Okay, and but just a thing, as I mentioned every time, don't forget to make notes. Today this time you are going to get a long weekend. Okay, so tomorrow also linear algebra is very simple, so take today's time, tomorrow's time, Saturday, Sunday, and also yeah, 4 days. Okay, so don't waste this 4 days. Try to go through at least go through the videos in 1.25 or sorry 2 or 1.5 speed. Okay, if you for example if you see univariate bivariate, they're simple, skip that. At least normal distribution and transformation, central limit theorem, mainly hypothesis testing. Okay, go through these videos or some blogs at least and make some notes and put it aside. Okay, you will use this all this in our next. That means NumPy, Panda, Matplotlib, machine learning. Yeah, in machine learning you are going to see all these details. Okay, so if you forget it about this, it will be very difficult for in those classes to follow. Okay, just make some notes and be ready for next modules. Okay, that's my suggestion. Okay, fine. Thanks, guys. Thank you so much. Let's meet tomorrow. Bye.